You're gonna have to take them out after you, right? Okay.
Wait.
Just a few more minutes here. Okay, let's do this thing here. So let's do it a different way this time. First of all, I'm going to calculate I infinity right away. So it's super important that I give you these symbols. If the circuit is obvious where there's one source, I won't give you these directions. But in this case, I don't really know what's happening in the circuit because I have these two sources. And it would take some time to figure it out. And I don't want to force you to do that. I want you to do the circuit. So I know the current's going that way, and I know the current's that way at 0 plus. So the first thing that I'm going to do here is I'm going to look at t equal to infinity. Now the first thing that I see here is that I'm going to do source transformation. If I do a source transformation, this is a 5 volt, that guy and that guy add. So my circuit really looks like this here. So I got a 2 ohm, I got a 5 volt, and then I have this guy, like this, and then I have my inductor with the source, with the resistor here. So why don't I do a source transformation here? It doesn't make any sense. Because then I'm going to get a current and a voltage in parallel in series with the inductor. That doesn't help me. So I'm just going to keep it like this here. And so now I'm looking at this guy here. That's what I want. So what happens here is that then at t equal to infinity, what I'm seeing here is that I'm seeing a 5 volt, a 2 ohm. I got it open here, so that doesn't mean anything as far as the current is concerned. Then I got my source here. Then I have my resistor. And you can see that this guy right here is this IL at infinity. So when I look at that IL at infinity, well, I just got a series circuit. So it's going to be 5 minus 4. So I got a 1 volt. Then I got a 3 ohm resistor. So then this tells me here that IL at infinity should be 5 minus 4 1 plus 2 should be 1/3 m. Okay? So that is my B value right there. So when I check my circuit, I'm expecting 1/3 of an amp. Okay, I'm expecting 1/3 of an amp. Now, since I did my source transformation, I'm going to continue to do that circuit right there. Right? So here we go. So what do I want to do? I want to relate 2 currents, 2 voltages. Here we go. So now I want to apply KCL and KVL at t equal to 0 volts. So when I look at this guy here, I'm seeing, what is this C value? 116. Clearly there's a split of the current, so I'm seeing the current of the 2 ohm must be the sum of these 2 currents right there. So if I look at here, so if I look at KCL, right, at the start right here, at that node, we can see here that it's got to be I2 has to equal IC plus IL. And I'm going to keep changing it now. Now note, this node right here, assuming I make this ground, has to be VC. So then that means that minus that gives me the voltage across this guy. So then this means here that if I just keep going on, this has to be what? 5 minus VC over 2 gives me that current. Then IC has to be 1/16 S hat VC. And then I get plus IL. Okay? So if I clean this guy up, I'm going to bring this to the other side. Damn, this is going to be messy. Right? So this is going to be 16 S hat VC plus 5 halves VC plus IL equals 5 halves.
Should be 1/2.
Yeah. 1/2.
It's 5 minus VC.
This should be, where am I seeing 1/2? Is this not 5 halves on this side?
It's
It is 5 halves on the right.
Oh, God, totally agree. Thank you. I would probably multiply that by 2
yeah.
just to clean it up a little bit, but I typically don't like to do that. But since I'm going to have to do a matrix, I multiply everything by 2, so I really have 1/8 S hat VC plus VC plus 2IL equals 5. I think that's a nice equation. Okay. So now, let's go do KVL. So if I do KVL, I got to do what? I got to relate these 2 voltages. And you can see that along here, that has to equal that. So VC has to equal the sum of these 3 right here. So then I'm going to say here that VC has to be, is in parallel with this branch, so it's got to be VL plus 4 plus the voltage of the 1 ohm resistor. So what do I got to do? I got to convert VL, I got to convert this guy. So here we go. So look what I'm going to do. I'm going to bring that VC over here. And you see that 4? I'm going to bring it to the other side. Okay? So I should get minus 4, and I should get minus VC. So then I'm going to start writing this up. So since I wrote VC first, I'm going to make that my first variable. So then I'm going to go minus VC, then I got VL. VL then should be, what's the inductance? Is it a 1 Henry inductance? Okay. So then it's 1, so I'm going to get S hat IL. And then I got this guy, but this guy is in series with the inductor, so it should be 1 times IL, so I'm going to get plus IL equals minus 4. Okay, that was... So now I'm going to matrix this guy up. Now I'm going to matrix up the equations. So since this is the first one I see here, so it's got to be, so it's this guy. So I'm going to go 1 plus 1/8 S hat, going straight down, minus 1, and I go to the i's. The i's should be 2. This I should be 1 plus s hat. And then I'm looking for my constant terms here, which should be 5 and minus 4. But before I do this, I want to make sure I double check it. Okay, let's see. So I got, that looks good. 2 minus 1, the sum of these, 5 and 4. Okay, so now I'm going to take the determinant of this guy. Okay, here I go. So look at this, I'm solving for the second variable this time. So that means I'm going to take this column, and I'm going to replace this when I get that term on the other side. So here we go. So I'm going to take the determinant of this guy, so it's got to be 1 plus s hat times 1 plus 1/8 s hat times this minus minus gives me plus 2 il. So now I get the coefficient term now. So then I get the matrix where I get this guy, so it's got to be 1 plus 1/8 s hat. I get minus 1. Now I replace this column with that column, so I get 5 minus 4. So let's see if I can clean this guy up. So I get 1 times 1 plus 2 gives me 3. So I'm going to write this guy right here. Right? So the way I typically do this to try to reduce errors is that I put symbols like that. Okay? So then the next term here, I'm going to go after the s hat terms. So I get what? S hat times 1 gives me s. And then 1/8 s hat times 1 gives me 1/8 s. So then if I come over here, I'm looking at only that term and that term. So if I look at that guy, so then I'm going to get s hat plus 1/8 s hat should be 9/8 s hat. So I get 9/8 s hat, like that. So now I'm going for the s hat squared term. There's only one, so I get that guy times that guy gives me 1/8 s hat squared. So I get 1/8 s hat squared. And so now I'm going to do this term. So what you're seeing here is that this operator equation is operating in this guy. So the first term is a derivative of that, so that's 0. So then I get 1 times minus 4. And then I get this guy. So I get minus minus 5. So then I should get plus 1. So what am I going to do? I'm going to clean this up. See that 1/8? I got to multiply everything by an 8. So that 8 cancels that. So I'm going to get s hat squared plus 9s hat plus 24. 8 times 3 is 24. IL equals 1. So then this should be 8 volts. So I'm saying this is my equation right here. Now, let's check this. Okay, so if I check this, so if I look for, so look at that, because I'm going to get tight over here, so I'm going to bring it right here. Okay, so look at here. I'm going right up here, and I'm going to do my check right here. So if I do my check at IL equal to infinity, I should get this constant B. What is that fourth term? That term is 0. The second derivative is 0. And then I get 24B equals 8, which then tells me that B is equal to 1/3, which agrees with this right here. Okay, so that's a small check. Doesn't mean you got the right equation, but it's a small check. Okay, let's go to the next one. Okay, we're looking at problem 5. So remember, I'm reluctant to give you one second order equation, because if you screw up that equation right there, I mean, you make me happy, but you're not happy. So this way, we don't stand the chance of having that problem. So if you screw up on this, you still got the other problem, right? Remember, go for the partial credit, right? Go for the partial credit. No, I don't. I only have the first part of it. I'm slacking off, there's no doubt. You know, I thought I was going to get through it really fast until I got to the second one. And the second one. Because like I say, I really try to find your errors. And it's really difficult for me to grade during the week. It has to be on the weekend. God, this thing is terrible. You know, one thing that I forgot to mention is that when you look at the question like problem 5 on the exam, you don't have to derive the equation. You got to trust me that this is right. I've seen people that didn't trust me, and you know what happened? They kept deriving it, they kept deriving the wrong equation. And so they spent like 20 minutes, and guess what? They didn't even do problem 5. You know, I don't want to say dumbass, but dumbass. Look, it's right there already. Solve the goddamn equations. Okay? I mean, am I being, I'm trying to help you here. But there's these people that, man, where's the goddamn love here? Right? There's like no love here. And I'm going like, help yourself here. God damn it. That's a problem. Okay, so IL of 0, 1. IL of 0, 1.
You don't need to.
If we
Because you know that this says that because of that. So that's
every so it's going to be A1.
oh
Yeah, I know. Everything I did is equal to my nose. That one this is why.
does this mean there's 0 so that makes it useful.
Yeah.
Just makes that wide. Makes it don't worry about it. There's no source of that.
The over R 20. Okay, how about if we do this? Okay, let's do this guy. So I'm going to assume that this equation tells me about this circuit. So you can see that at t equal to 0 plus, the switch is thrown open and it kills off this 20 volt source. So the 20 volt source only comes into determining the initial condition of the inductor. But the whole goal is to figure out this guy. Now note, I gave you the inductor equation, so I'm assuming that you're going to pay attention to the inductor equation, not the capacitor. So now what we want to do here is that at t equal to 0 plus, what we know here is that we got this guy right here. So we got this 4 amp, then we have this 1 ohm, 1 Henry, 1 farad, and that's that. So note, if I give you these nice numbers like this, you should not expect nice solutions, right? I'd rather give you nice numbers so that your equations are real nice and easy to deal with. So, here we go. So that equation describes this guy. So then, I'm going to start the thing here. So the first thing I got to do here is that I got to determine the general response. So if I look at that general response here for the inductor, I'm going to have some natural response, which I don't know what it is yet, because I got to go and solve the characteristic equation, but I have this B constant because I have a source. Let's go calculate what the force response is. So, what is B? So I gotta look at that circuit. At steady state, that's 0, that's 0. So then I get B equals 4. So this immediately tells me that B must be 4. Right? That's a nice equation that tells you that. Okay, so now I got B. So now I got to go determine the natural response. So now I'm going to determine natural response. So what that means here is I have to deal with the characteristic equation. So then that means I deal with this thing when the sources are 0. So I go like this. Right? And then this will be the natural response. And I look at that guy, you can see I'm going to divide everything by 3. So if I divide everything by 3, I'm going to get s hat squared, s hat plus 1/3. That has to equal 0. So off the top of my head, there's no solution that I could see where I could break this up and get the solution. So what am I going to do? I'm going to compare it to this guy. Right? So if I make the direct comparison between this and this right here, what you're seeing here is that 2 alpha has to equal 1, which tells me that alpha has to be a half. And if I look at this guy, omega naught squared has to be a 1/3. Okay, I don't know.
Omega's pretty awesome.
Okay, thank you.
0.57.
Yeah, I can't do this in my Thank you. Okay, so then we're going to say that omega is greater than alpha, so that means it's underdamped. So that means I got to calculate omega d. So what's omega d here? Omega d has to be omega squared minus alpha squared. So that has to be what? 1/3 minus 1/4. Oh yeah, I can see that that has to be the case. So if I clean this up here, it's going to be what? 4 minus 3, 1, 12, so it's the square root of 12. So I'm going to leave it at square root of 12. I'm not going to mess with this. So now I got omega d. Okay? I got omega d, right? In fact, I could write it, I guess, as 2 times the square root of 3. Something like that. Yeah, I could do that. But I'm not going to do that. I'm going to leave it right there. So then, that means that my general response here is going to be IL of t is going to be e to the minus alpha t. What's alpha? Well, alpha here's a half, so it's got to be minus t over 2 times the quantity a cosine t over the square root of 12 plus a2 sine t over the square root of 12 times plus the quantity 4. By the way, one of the biggest errors that I saw on helping people with the problems is that they didn't include B. If you don't include B, then your A1 and A2 get screwed up. Okay, so now what do I got to do? I got to go find the initial conditions of IL to get A1 and A2. So now I need to calculate IL of 0 plus and S hat IL at 0 plus. Remember, this is the tricky one right here. So let's go calculate I. So what I need to do here is that I need to look at t equal to 0 minus, because I want that guy right there. So here we go. So when I look at the circuit, you can see that I get that 20 volt guy right here. So let's look at that. So I'm assuming steady state now, of course. Okay, in steady state, note that the 1 ohm is parallel to the inductor, so what happens? It shorts it out. So there's no 1 ohm right here. So then I get this guy here, so I get a short, and then I get the 1 ohm. Look how nice that is, right? Look at that. That's parallel to this. So I immediately know what the current of the inductor is, right? Because the current of the inductor has to be the current to that guy, so we already know that's got to be what? 20 amps? Wow. Oh yeah, because we got low values. Okay, so then I go to the next one. The next one, I have the resistor, but that gets killed off because VC here has to be 0 here. So isn't that nice? We're done. Right? Because this guy is in parallel to that, which is 20 volts. Am I messing up or what? I want to say that's 20 volts.
Yeah.
And then I get this 4 amps here. Yeah, dude, we're done. Just writing it out. So this is a nice circuit here, right? So we agree that IL of 0 has to be the current of the 1 ohm resistor, which has to be 20 volts divided by 1, so it's got to be 20 amps.
Before either, because it's controlled by the UT.
Oh, I thank you. See, I'm not listening to my own self. This is gone. It becomes an open. Only voltage sources become an open. Yeah, but it wouldn't have mattered anyways. So then when I look at this guy, we could see that VC of 0 minus is parallel to the 20 volt. So I get these two values right here. Okay, here's that. So now I got to calculate, that's how, this guy. So now we calculate, and this is the one that you want to be worried about right here. Right, that's what we want. So how do I get that? I got to go to my first two, so I need to look at the 2 first order equations. So if I look at the first 2 order equations, is there an equation that has S hat IL? This one does, this one does. You got 2 equations, 2 unknowns now. Okay? See, this is the one, this is the worst type of boundary condition because you can't just go and pick it out. So here we go. Let's go get it. So now what I have here is that I got VC, then I got what? Plus IL plus S hat IL equals 4. And then I get what? 1 plus, is that 2 s hat? So let's do, 1 plus 2 s hat VC, and then I get minus s hat IL equals 4. So you know what I'm going to do? I'm going to matrix this guy up. Right? If I matrix this guy up, it's got to be s hat, 1 plus 2 s, 1 plus 2 s hat. Then I'm going to get, this will give me 1 plus s hat, and then this is minus 1. So I just got to get, how do I write this? You know, that's not the way I'm going to write it. I'm writing it as a matrix operator equation. It's not an operator equation. Okay? I got to erase what I just wrote. But I am going to matrix it up. What I have here is that I have this. Technically, what I have is I have s hat VC at 0 plus. That's a number. And then I have IL at 0 plus s hat IL at 0 plus equals to 4. So, I mean, there's a bunch of ways that you can do this. I typically prefer the matrix algebra. So then I get this one, so then I got VC of 0 plus 2 s hat VC of 0 plus minus s hat IL of 0 plus equals to 4. Now probably the easiest way that you'll probably see here is you see this guy right here. I got to eliminate it. So what am I going to do? I need to plug it right into here. Or I could treat this as a matrix equation, which is what I prefer. Do I know that number? Yeah. What's that number? IL 0 is 20 amps, so I'm going to take this to the other side, and I get what? I get negative 16. So now I have one equation that looks like this. S hat VC plus S hat IL equals 16, negative 16. Okay? Now I'm going to look at this guy. So is that a number? Yes. That's 20. So what am I going to do with that 20? I'm going to bring it to the other side, and I'm going to get negative 16. So now I have 2 S hat VC minus S hat IL. So here we go. I'm going to matrix this guy. I got 1, 1, 2, minus 1. I'm going to do this S hat VC, S hat IL, and then I'm going to get negative 16, negative 16. So I want to calculate IL. So what do I do? So IL means that this has to be what? I take this column and I put it right into here. Okay? So then I get so this guy's got to be 1, 2, negative 16, negative 16, and then I take what? The determinant of this side. So this is what? So this is going to be 1 times negative 1. I get negative 1 minus 1 times 2, negative 2. So I get negative 1 minus negative 2 gives me negative 3. Oh, by the way, I forgot to put S hat here. So then I do the multiplication now. So then I get S hat IL of 0 plus will then be this determinant here, which will be what? Negative 16 positive 2 times 16, which gives me 16. So I get positive 16, and then I get negative 3, so then this becomes 16 amps per second for S hat IL 0 plus. So now I apply the solution. Now remember, there's lots of ways to do this. I like this method because I know I could do it on the board. So, here I go. So now I'm going to apply initial conditions to get A1, A2. Do I got it in the switch? Should I go all the way over here? Or you two?
Outside.
Okay, I'm just
Walking away.
you're glad. Okay. So here we go. So IL of 0 plus we saw was 20. So I'm going to apply that to this equation right here. So here we go. So we go IL of 0 gives me e to the 0, which is 1. Cosine becomes 1, sine becomes 0, so I get A1 plus 4. So I get A1 plus 4, which tells me that A1 must be 16. Okay. Now let's go to the next one. The next one is S hat IL of 0 plus. What did we calculate? Minus 16 divided by 3. Now I'm assuming that, okay, we should double check this to make sure, because otherwise it screws up everything. So, let's see. If I matrix this guy up, we agree that this is 20. I bring it over here, I get negative 16. This is 20, I get negative 16, okay? So if I look at this guy, I got 1, 1, 1, 1, 2, negative 1. I go negative 1, negative 2, negative 3. I bring this in here. I get negative 16. Positive 32 gives me positive 16. Oh, but I got a negative. Okay, so I'm going to say that looks good to me. Okay? So now, let's apply this now. If I apply this, that means I got to take the derivative of this thing. So let's be clever with our derivative. If I take the derivative of this, I'm going to get minus a half. And then I set t equal to 0, so that's 1. Okay? So then I get A1 plus this guy here. Oh, the chain rule tells me like this. So I got to be careful here. So the first one gives me minus 1/2. And then I set t equal to 0 in here. So I get A1, and then I get 0. So I get A1 for the first term. Now, I use the chain rule and I take the derivative of this guy here. So this guy becomes a sine, and sine of t equal to 0 is 0. So now I'm focusing only on this term. So this becomes a cosine, so then I get what? Cosine, but then I take a derivative of this, so I get 1 over the square root of 12. So then I get plus 1 over the square root of 12 times A2. So then I get 16 over 3, and then I get this guy. So A1 is 16. So look at that. 16 divided by 2 gives me negative 8. And then I get this plus 1 over the square root of 12, A2. Okay, you're going to have to help me with the numbers here. Let's see how I do. So if I bring this 8 over here, that's the same as 24 over 3, which gives me 8 over 3. Positive 8 over 3. So I get 8 over 3, and then I got to clean this guy out. So then I multiply both sides by the square root of 12, and that gives me A2. Okay? Now let's put this all together. So now, that means that the general response here tells me the following thing. That means I have the current of the inductor looks like what? It's e to the minus t over 2 times the quantity A1, which is 16. So I get 16 cosine of t over the square root of 12 plus A2, which is 8 over 3 square root of 12 sine of t over the square root of 12 plus 4. But that's not what we're solving for. Right? That is not what we're solving for. What we're solving for is that guy right there. How do I solve for that current? How would you solve for that current? Where would you use KCL? I mean, I could use it right here. Right? If I apply KCL, that's a messy one, you know? Yeah, dude, there's no choice. I don't see any choice. Okay, there we go. Right? Here's when you're taking the exam, you're going, that SOB. Yeah, I want to take care of everybody's going to his, walking to his car. Let's apply KCL here. Okay? I'm going to apply KCL. So clearly I can't give you a question like this on the exam. Because that could be, you know, a knockout punch right there. I'm not interested in that. Right? I'm interested in never seeing you again. Okay, here we go. So now we're looking at this current here. We agree that the currents have to be coming this way. Right? Because I only have a current source, and that current source is flowing like this. So if I look at that here, it's got to be I1 ohm has to be I1 ohm plus IL. And now clearly we have two different ILs. So this IL, I1, has to be the voltage of the inductor. Right? So this guy has to be, this is what I mean by this is messy. I gotta take the derivative of this thing. Damn. Okay, here we go. I'm gonna put this. Could I just say that this is left as a student exercise to the student?
It's like the math problem.
Right, it's just a math problem now. The issue is here is that I want to get its final steady state. Right? Its final steady state has to be equal to what? It has to be equal to 4 ohms. Is that right? Oh, it is. That's a good sign, right? That guy's open, that guy shorts this guy out, so then this guy gets all of the current. Should I do it? I'll do it. Yeah, I'm seeing some nodding heads here. We could stop right here, and if you don't want to see the end of it, you could go, right? But some people are shaking their heads, so I'm going to do it. Here I go. So the first thing that, see that IL, I'm going to put right here. If I put that IL, it's got to be 4 plus e to the minus t over 2. So you see that 12? I'm just going to call it omega d, so I don't have to write the square root. So this is going to be the quantity 16 cosine omega dt plus 8 square root of 12 over 3. Can I reduce that? That would be 2 square root of 3. No, and then I would get 16 divided by the square root of 3. It doesn't really matter, right? So then I'm going to get sine omega d t, and then I got to take the derivative of this guy. If I take the derivative of this guy, it's got to be what? That's gone, it's only this guy. So then this derivative tells me it has to be what? The inductor value is 1, so I don't have to worry about the inductor value. So now I take the derivative of this thing. Okay, here we go. So it's got to be what? Minus 1/2 e to the minus t 1/2. And then I get this whole thing the same, exactly the same. Actually, look at that. These two terms add. Look at that. That's 1, that's minus 1/2. So I get 4 minus 1/2 for that. No, plus 1/2. Right? So you know what? I don't care about that term. Right? Because we can add them. So now it's the chain rule that we got to worry about. So the chain rule says I got this guy. So I got e to the minus t 1/2. Now I got to do this. So it's got to be 16 square root of 12, right? I'm going to get sine of omega d t, but I get a minus sign since I took the derivative of the cosine. This guy, look at this. So if I bring this guy out, that 12 and that 12 cancel out. I'm going to get plus 8/3 cosine omega dt. Actually, that's bad. Okay? So now if I just combine these together, if I combine these together here, I'm going to get, right, I1 ohm is going to be 4 plus 1/2 e to the, can I bring in the 1/2? Look at that. If I add that and that, that's a half. So that half gives me 8, 4. So I'm going to get e to the minus t over 2 times the quantity 8 cosine omega dt plus 4 square root of 2, no, that's square root of 12, times 3 sine omega dt, and then I get this term right here, plus e to the minus t over 2. You know what? Let's combine terms, right? That factor and that factor are the same, so now I got these right here. So what I'm going to do here is that I'm going to put this right underneath here. So then I'm going to get plus 8/3 cosine omega dt. And then this is minus, so I get minus 16 square root of 12 times sine omega dt. So then I just got to clean this up. So if this is 8/3, this should be 24/3. 24 plus 8 should give me 32. So I then should have 32 over 3 cosine omega d. Then I'll look at this guy. Damn, that's messy. Okay. I would do the algebra here. Let's see if we could do this in our head. Is that the same as the square root of 3 over 2? Right? So what I would do then, I would do 2 times the square root of 3 here. That gives me 8 times the square root of 3 divided by 3. But the square root of 3 over 3 is the square root of 3 at the bottom. Now, the reason why that's nice here is that I could get a square root of 3 terms over here. So look, this is 2 square root of 3, so that should be 2 into 16 gives me negative 8 over the square. Oh, is that right?
It's fine.
Yeah.
Right? Is my algebra right? Damn. I'm seeing the solution. I'm not really checking my algebra here, right? But this is 32 over 3 e to the minus t over 2 cosine omega dt. So if I was to plot this thing, how would I interpret it? Well, I know that it's got to go to 4. And you can see that at t equal to 0, this has to be 4 plus 32 over 3, which is 44 over 3. Is that correct? 44 over 3, that's way up there. So what was this current initially? Have to be 1/20th. So you can see that this current had to be something like this. It's coming in initially at 1/20th of an amp is I1 ohm of 0 minus. And then what does it do? It jumps up to 44 over 3, which is way the hell up there, right? That's what? Like 13?
Yeah.
Yes.
Didn't we get just 20 amps initially?
Yeah.
Not 1 over 20?
Was it 20 amps? Oh, thank you. We did get 20 amps. Where am I getting 120? So then, now I gotta pay attention to this. So it's 20, and then it goes to like 13, 14, a little over 14. So we'll say it's approximately 14. That's a decay. Right? So then it's going from 20 and then it's jumping down all the way to about 14. And then it looks like around 14 it's going to exponentially decay like that. Now, whether it's going up or down, it looks to me like it's got to be going up. I don't know what the spike is. Is the spike down or up? We'd have to calculate the local max or min. I'm not going to do that. So if I was to plot it, it could be either going up or down. I don't know. But I'm guessing it's coming down like this, and then it's going to oscillate like that. And there she blows. Yes?
So doesn't it eventually decay to 4? So it immediately drop to 14 and oscillate down to 4, right?
Oh, thank you. He's absolutely correct. So it immediately drops down to 4, and then it oscillates about 4. Yeah, we said that beforehand, and I totally got lost. So maybe it goes like this, and then we decay like that. That's for the current of the 1 ohm. Okay, I'll see you at 9:20 on Monday, right?